Okay, so that was the definition of a linear representation. Next, we come to a matrix representation. And we will spend a lot of time in the rest of this course working out the features of the matrix representations. Okay. So now consider the vector space Vn. Now, if we introduce say a basis, on Vn, then we can represent the linear representations of our group as n by n matrices denoted by, say, D of G. Okay. And the set of these matrices D of G for all G in the group, this set is called an n-dimensional matrix representation. Of the group G. Okay. So if I define some orthonormal basis say E1, E2, En in Vn, then the action of T of G on E of K, define the representation, define the D matrices in the following way. T acting on E of K, take me to D, so T is a function of G. So it's going to give me I times K acting on E of I. Okay. So then in this basis, this equation X, can be written as if X is, say, X is Xi times EI, then this equation becomes Xi prime sum over J, D of Ij, which is a function of G, X of J. Okay, so in the Einstein convention, which is something we will be following, we can write this as xi prime d of ij of g acting on dj, right? So these are the representation, matrix representation of the group G. Okay? Because this is just following what we know from linear algebra. In linear algebra, we know that once we choose a particular basis on our vector space, the linear operators can be given the form of matrices, right? And here we are doing exactly that for the linear representation that we talked about above. And the matrices then become these D matrices. Okay? I'm just going from abstract to less abstract. Okay, so now that we have defined what matrix representations are, let me formally define what a matrix Lie group is, okay? A matrix Lie group is a group that is defined in terms of a set of matrices I guess labeled by a set of continuous parameters this matrix representation of the Lie group is also called the defining representation. Okay. For matrix groups, there is a particular representation which is, a formulation of that group in terms of matrices, which are called the defining representation. It's a little circular, if you ask me, but I think it's okay. So, for example, the group SU2 is defined. Its matrix, its defining representation is 2 by 2 unitary and unimodular matrices. Okay, we know that the matrices of SO3, there's a homomorphism between SO3 and SU2. So that's a different representation of SU2. Okay, we can think of it as its own group, but we can also think of it as a matrix representation.
Does unimodular mean determinant one?
Yeah. Sorry. Yeah. This means, or maybe I should. Yeah, it's the modulus of the matrix U, right? I mean, that's a generalization of the determinant is the generalization of some of the modulus of a number, right? Or maybe I should just write, yeah, so. I think it's fine, yeah. So we have, we understand what a matrix Lie group is, but although I have talked about Lie algebra, I haven't really shown that the Lie algebra is kind of the natural structure that follows from the matrix Lie group. So that's something I want to show next, okay? But before that, can we have some questions or comments?